Today the topic is performance analysis of rooftop solar photovoltaic system in composite environment. My name is Arun Kumar Maurya, Assistant Professor in the Department of Electrical and Electronics Engineering at AKGEC Ghaziabad. So as far as the content is considered, first one is introduction, pictorial diagram of grid connected solar photovoltaic systems and its block diagram and the growing trends of grid connected solar photovoltaic system over the globe, its graphical representation of grid connected solar photovoltaic system and its performance analysis throughout the year, and their results and discussion and the conclusions. So in the intro part we have seen the in nowadays the demand of renewable energy sources is high. And why the demand is high? Because the uses of these type of sources are too much as compared to the other sources. So solar photovoltaic system, wind energy, biomass, fuel cell, these are the best alternatives to meet our current demand as compared to the supply. So in this paper, the concept of injection photovoltaic power into the utility grid has earned widespread acceptance in these of renewable energy systems, its generation and the distribution side. Renewable energy is increasing considered essential for meeting current and future energy needs, which I have described here. Photovoltaic power as a clean and unlimited source of energy that is taken from the sun is probably the best technology amongst all the renewable energy sources, and therefore a considerable amount of research and why for since it attracted the attention of policy makers and the researcher also. The better utilization of the photovoltaic power to the grid, interconnection of solar photovoltaic system is needed to our existing applications. Government is also focusing and also subsidize things to the uses of solar photovoltaic system. Photovoltaic power rendering to the utility grid has been fastest growing renewable energy technology. Grid connected inverters have evolved significantly with high diversity. If we talk about the other parameters, the efficiency, size, weight and the reliability, we may see there are the three terms CIA: confidentiality, integrity and the availability. So when we talk about these things, the reliability point of view in terms of efficiency is also seen by this. It have all improved significantly with the development of modern and innovative inverter configuration, and all these factors have influenced to the cost of producing inverters. There are a lot of research is going on to the different types of inverters used for better applications to increase the efficiency as well. So this is the pictorial diagram of grid connected solar photovoltaic system. These are the panels. So this is string 1, this is string 2, we may easily see. This is high quality DC to AC inverters. So inverters used for to convert DC into the AC supply. These are the isolation switches, and this is AC circuit breaker box, and these are the household sockets. And this is a energy meter, that is a smart energy meter, which displays all the used and available power, voltage, uh, frequency, and all the things. And this is the grid side. The supply is going to the electricity grid. So this is the pictorial diagram of grid connected solar photovoltaic system. So this is the GIF pictorial and the videographic representation of the process of solar photovoltaic system to the grid, the transfer of energy from sun, and which is fed into the grid side. So we may easily see. So if we talk about the basic block diagram of grid connected solar photovoltaic system, so this is the typical and the simple layout of grid connected solar photovoltaic system. The first one is photovoltaic array. This is solar panel we may easily consider, and this is the power electronic surface. So I will talk about it. The first one is DC to DC converters. So DC to DC converters are nothing like that, but it used for to maintain for the variable insolation of the light to a constant insolation, which we use DC to DC converters. There are so many types of DC to DC converters are available: buck boost converters, and sapig zeta, and sparse matrix converters. There are so many converters are used for this application. Other one is DC to AC converter. So this is nothing like that. It's a inverter, which we are talk about in the previous slide. So there are so many types of DC to AC converters, that is DC to AC inverters, voltage source inverter, current source inverters, multi-layer inverters. There are so many types of inverters. And this is MPPT, maximum power point transfer tracking. This is MPPT, maximum power point tracking. This is based on the we have studied the maximum power transfer theorem. IPSO, basically it is improved particle swarm optimization techniques. MPPT is nothing like that. It's a controller which maintains the instantly the maximum power throughout the operation of the conversion of the supply. And it's a control mechanism, control technique to control the DC to AC converters and to voltage level of VDC, and the supply is given to the grid side. To get the maximum power from the photovoltaic panel, that is solar panel, at the prevailing temperature and the insolation conditions, either the operating voltage or current should be controlled by a maximum power point tracker. Basically this is MPPT. That should meet the following some conditions: operate the photovoltaic system close to the MPP, maximum power point, irrespective of the atmospheric changes, and it's having low cost and high conversion efficiency, provide an output interface compatible with the battery charging requirements. Its efficiency of a solar cell is less. It only converts 15 to 20% of the sunlight energy to the electric energy, But while using of MPPT technique, the efficiency of a solar photovoltaic cell increase by approximately 20 to 30%. It's a uh, very good option to use the MPPT techniques. There are a lot of MPPT techniques. We may see VMPPT, voltage based MPPT, current based MPPT, P&O technique, and the incremental conductance techniques. There are so many techniques are available in the study. So I have already told the what is the use of MPPT. So it is a technique used to extract the maximum power from the solar system at the current weather conditions. MPP, that is maximum power point. It is an operating point at which maximum power can be extracted from the system. So this is the typical layout of how the MPPT works. So this is the on-site and the rooftop pictorial representation of the solar photovoltaic system. So this is the comprehensive details of the solar photovoltaic system. The 40 kilowatt peak of two units, each of 20 kilowatt peak PV system has the number of solar modules, each unit having 68 modules, and each module is made up by Apex Solar India of 300 watt peak capacity, having 72 solar cells made of polycrystalline silicon. The modules are 300 watt, each of 300 watt capacity, having the solar cell made up of the same silicons are used in the photovoltaic system. The modules are free from any effect of shades, are fixed with an tilt angle of 21 degree facing south to an azimuthal angle of 0 degrees considered. A three-phase transformer based inverter make of Delta Electronics Private Limited model M20A is used to convert DC into AC, which is directly fed into the grid side. So this is the meteorological observations of the site. I have analyzes the around a 1 year data as seen the ambient temperature and the irradiance in every month. This is the total mean data of particular month. So in April we have prepared that data from 1st April to the end of the April and the end of the day. So in April the ambient temperature that is 28.97 and the irradiance 5.62 kilowatt hour per meter square. In the May 29.9 and 4.8 for the irradiance data. In June that temperature is high, it is 29, 4.94 is the irradiance. In July 26.86 and the 4.36 is the irradiance. We may see and observe that data easily by the month of year. So this is the performance analysis. The IEC, International Electrotechnical Commission, IEC, published the several standards such as IEC 61724 in 1998, which describes the few specified parameters for evaluating the total and overall performance of the solar photovoltaic system in a particular region. This standard has been accordance with the Bureau of Indian Standards, that is BIS, in 1998 to analyze the electrical performance of the present grid connected solar photovoltaic system. Some parameters like that array yield, final yield, reference yield, that there are several losses, capture loss, system loss, and the other factors. Performance ratio were studied by computing the actual data collected during the assessment period of a 1 year. So the first parameter is array yield. The array yield is defined as the ratio of energy output from a photovoltaic array over a particular period, in day or a month or a year, to its the rated power. This is the rated power of a solar panel. And EDC, what is EDC? EDC is the output from a solar photovoltaic PV panel. So the array is calculated as Ka. A is as it is the suffix for the array yield. This is final, and the other one is final yield. The final yield is defined as the ratio of net daily, monthly, or annual AC energy output of this entire photovoltaic system, which was supplied to the array, to the rated power of the installed solar photovoltaic PV array. That is KF is equal to EAC divided by the VV rated. And the other one is reference yield. The reference yield KR is defined as the total daily in plane solar irradiance that is computed by HT over the GI reference, and it's a reference radiation constant that is taken to be 1 kilowatt per meter square, and the area is 77.6 meter square to be considered. And the other one is PV module efficiency, KPV, equal to PDC divided over GT into AM into 100. The other formula is to be calculated of the photovoltaic module efficiency, equal to zeta T into 1 minus beta reference, which is further multiplied by that difference of temperature. Eta D reference, what is this? This is the efficiency of photovoltaic module at a reference temperature. Beta reference, that is a constant of power. T reference, it is the reference of temperature, and the capital T, it is the cell temperature. And capital T is given by the T ambient temperature plus normal operating condition temperature minus 20 multiplied by Ct by 100. So this is to the computation of the capital T temperature, and we will calculate it. And T reference is given, and this is given. We may easily see the eta T for the PV module efficiency, where T ambient and the NOCT, that is nominal operating cell temperature, it is already discussed by me. And other point is inverter efficiency. So the instantaneous inverter efficiency is given by the PAC divided by the PDC. So this is the formula to calculate the inverter efficiency in terms of the AC power divided by the DC power. It is the output divided by the input power. And the monthly inverter efficiency is calculated as inverter efficiency EAC into D divided by EAC into D multiplied by 100. System efficiency, the overall instantaneous system efficiency is given by K system equal to eta PV into eta inverter. Basically it's a efficiency. So the total system efficiency is represented by the K system into D equal to EAC into D over HT into AM. And the and the most important point is performance analysis of the overall system, that is to be calculated as the KF by KR. This is final yield over the reference yield. This is final yield and this is reference yield. So performance ratio is also calculated by the system efficiency of K and the KSTC. This is also calculated by this formula. Other point is capacity utilization factor, that is CUF. It is defined as the ratio of actual energy generated by the solar photovoltaic system to the amount of energy to the photovoltaic system would generate if it's operate at a full rated for 24 hours per day for a year, and it is denoted by the EAC divided by the photovoltaic rated power into 24 into 365. We may see that full rated power for 24 hours per day for a year. So this is CUF, and this is calculated by the another formula, peaks and hours per day per 24 hours per day. And other point is energy loss. So there are the various loss encountered while considering the solar photovoltaic system and its performance analysis. So losses are also important to see the overall conditioning of the solar photovoltaic system. The different losses in a photovoltaic system include area capture loss, system loss, and the soiling and the degradation loss. The first one is capture loss, that is LC. It has two breakups, two components, that is thermal capture loss LCT and other one is miscellaneous capture loss LCM. So the thermal capture loss and the effect of cell temperature on loss is denoted by the minus gamma TTC minus 25, and the normal working temperature is to be taken as 25 degrees centigrade, where Tc equal to the cell temperature, Vt gamma equal to the coefficient of temperature, which is to be calculated as the L temperature maximum 492 Ta minus 4.405. These all the specified parameters are described in the IEC 61850. We may see 61724 and 61850. And this is the subsections of the terms. So, and the other breakup is miscellaneous capture loss. This loss includes cable loss, Joule effect of wiring, shading effect, and the mismatch loss, degradation loss, and the capture loss is denoted as LCT plus LCM. LCT is the summation of to be taken as ICT, and LCM is ICM. LC equal to KR minus KA. So it is the overall annual analysis of monthly mean energy yield in April, May, June to the March. So the ambient temperature around the year is 24.03. It is the average of all the months, which is taken to as a mean. And DC DC energy, DC power is the mean is 154.35 kilowatt hour per day, and EAC equal to 136.76 kilowatt hour per day. YF, YR, YA, LS, LC, and total losses are described here. So These are the results and discussions. The performance result of the solar photovoltaic system is discussed in this section in a broader way. The monthly average solar radiation on the tilted PV array indicates the solar radiation is the minimum during the month of November, 3.05 kilowatt per meter square, and it is the maximum, that is 5.62 kilowatt per meter square. The annual mean of monthly cell temperature varies from 14.76 to 29.9 degrees centigrade. The maximum and minimum average monthly energy yields are 5972.35 kilowatt hour in April, in the month of April, and it is minimum, it is 3099.2 in the January, respectively, based on the weather conditions. And also there are some other factors to see the analysis and the performance of the solar photovoltaic panel. So this is the graphical representation of annually observations of energy yield. So it is the annual energy yield graphical representation in the April, that is 3099.2, in the May 4308. This is the overall annually data. Based on the parameters available to us and the experimental investigation, the mismatch losses are brought to be considered in the month of January to the December. For a 1 year, we may easily see in the December the losses are maximum 180.08 kilowatt hour in the month of December. I think the minimum is 14.9 in the July. So these are the two observations of mismatch losses for a year while we consider. This is the monthly mean module inverter system efficiency, energy yield to the grid losses and performance ratio, which I have discussed in the previous slides. So for a 1 year calculations, the module efficiency, inverter efficiency, and the system efficiency, and the corresponding losses for a particular month, which is the mean, and the total solar photovoltaic system, the performance ratio is to be taken as in the April 0.88, May 0.87, June 0.71, July 0.79. So this is the total overall performance ratio parameters. So that the advantage of the mean of that is the 0.79, that is 0.8 performance ratio is computed based on the observations and the analysis of experimental data. It is the average monthly energy to the grid losses and performance ratio. It is the graphical representation. Results after the experimental investigation while considering the solar photovoltaic system, which the power is injected to the grid. The 40 kilowatt peak grid connected solar photovoltaic system installed in the northern India is observed for a period of year. The significant obtained results output from this experimental analysis are mentioned as follows. The final output factor of this system is 3.41 hours per day. The mean module performance and the converter performance parameter, which is the efficiency, that is to be come out to be 13.48 and 93% approximately. The mean system efficiency parameter obtained is 12.53% with annually supply of about 4.15 megawatt hour to the local grid. The performance ratio is obtained as 0.79, which is approximately near to the zero point 0.8. Hence, the proposed and installed rooftop solar photovoltaic system is needful for the reliable solution for a global level. So, some are the conclusions from my side. The 40 kilowatt peak grid connected solar photovoltaic system installed on the rooftop is monitored around a year, and its monthly and annual performance parameters are described and studied in a comprehensive manner. Although the solar photovoltaic market experienced the astronomically levels of growth and the cost reduction in the recent years, there are many technical challenges and the economic realities that need to be reconciled in order for the DG resources like grid connected solar photovoltaic system to be at a priority with conventional generations. For successful and the mass adoption of the system, new technologies must be developed that will allow smart inverters to do more than just a provide to DC to AC converters. When we see the comparative analysis of the traditional inverters, modern grid interactive inverters will need to provide the good volt per bar control, power factor, and the voltage stabilization, frequency regulation, and the enable storage and utilize more and modern communications protocols, all at a reasonable cost. This new generation of the inverters and the converters that we have studied in this research, and the total performance analysis while considering the grid connected solar photovoltaic system has been rightly termed the use of smart converters, that we smart inverters DC to AC and AC to DC depending upon the conversion of supply. The future of grid connected solar photovoltaic system design will require inverter to monitor, react to adjust their output based on the instantaneous feedback from the grid. The inverter will also be able to save and share the data with facility to management system for trading, predictive, preventive, and the corrective maintenance. So in the solar power, it has the potential to become one of the main contributor to the renewable energy sources for a future electricity supply with a several advantage. Just like that, it is pollution free, and low maintenance cost, low operational cost as well, with no supply limitations are existing. This improvement in technology and continuous growth of the solar photovoltaic market has led to the drastic reduction in the cost of solar photovoltaic system on the global market, as work is done to increase the conversion efficiency, which I have described. That different type of smart inverters are applicable to see the fast and good response to DC to AC conversion. So these are some references to carry out the research.